Hello everyone. We will now begin our lecture on chapter 16, which is on the analysis of variance. It's also called ANOVA in short. AN is derived from the first two letters of analysis, and then O from of, and VA is the first two are the first two letters from variance. All right. Now, this study is about comparing multiple means. Now, chapter 10, we had learned about comparing two population means. In chapter 12, we had talked about comparing two proportions. This time, we are going to talk about comparing multiple means greater than more than two means. So it could be three means or four means or more than that. Any number of means can be analyzed using the ANOVA testing, ANOVA analysis, and that's what we are going to learn in this chapter, how to go about doing that analysis. Now, the first section of this chapter talks about a different kind of distribution that we are going to use in ANOVA analysis. It's called the F distribution. Right, so we are going to go through that distribution first, understand what that distribution is about and what the properties are, and how the formula to calculate the F statistic, what the degrees of freedom formula is. So we will go into that in section 1 of this chapter. Now here are two different F curves given to us. One is the orange one and the other one is the blue one. And as you will note that these curves look pretty similar to what the chi-squared curves were that we learned about before. The F curves are all hinged at 0. So 0 is the lowest value that F can take. All right. So it starts at 0 and then it goes up, kind of peaks more towards the left, and then they have a long tail to the right. So they are not symmetrical curves. They are right skewed curves. All right. And that is also the same as with chi-squared curves. Another thing that we notice is the DF values. Instead of DF having a single value, it has two values, 9, 50. All right. So the DF for F curves have two parameters. The first parameter is called the numerator value, and the second one is called the denominator value. And there are formulas to calculate the numerator values and the denominator value, which we will learn about later. But for this case here, for the orange curve, the DF is 9, 50, and for the blue one, it's 10, 2. And just like with the T curve or the chi-squared curve, with the F curve as well, as the DF values increase, the curves look more like a normal curve, but keep in mind they are not normal curves. Especially F and chi-squared curves are hinged at 0. They do not take negative values like with the Z curve or the T curve and the T values. All right, they don't take negative values. They start from 0, and then the F values will keep increasing, and the tails of these curves, as they approach the horizontal axis, they get as close as possible to the horizontal axis, but they will never cross or touch the horizontal axis. Now here are the basic properties of F curves. The first one says the total area under an F curve equals 1. And that is true for any distribution. All right, the total area under the curves will always equal 1, and the same is true for the F curves. Property 2 says an F curve starts at 0 on the horizontal axis and extends indefinitely to the right, approaching but never touching the horizontal axis as it does so. And as we saw in the diagram before, the F curve begins at 0. It starts, the lowest value that an F value can take is 0, and then it increases. All right. And property 3 says an F curve is right skewed, and that is the same as with chi-squared curves. They are all right skewed curves, and therefore the testing that we will perform will always be right tail tests. Okay. Let's go over the F table that you will be using to work on the problems on ANOVA tests. You see over here, the table has 2 degrees of freedom. One is called the numerator, so DFN, as you see here, this DFN, that N stands for numerator, which is going to be the first parameter of the DF, degrees of freedom. And then we have what's called the DFD, and this last D means denominator. All right, so the numerator parameters are listed across on top, and the denominator ones are listed in the first column. And then the next column has all the special alpha values. So 0.10, 0.05, 0.025. These are the special alpha values we commonly use for hypothesis testing as significance level for alpha, or in the case of confidence intervals too. Right, so these are special values again because there is a unique F curve based on the sample sizes. We will just have to work with a truncated table. All right, this table will not give us all possible F values based on their sample sizes. For that, you will have to use your calculators or a statistical tool which will give distributions for any values. All right, and then here in the body of the table are the specific F values. So just for example, if we are looking for F of 0.025 with DF, and we'll talk more about those parameters for DF, numerator and the denominator parameters, but let's say that the numerator value is 2 and the denominator parameter is 5. Okay, how would we find the F value of 0.025 with DF2, 5? We first have to go down the DFD column, and the second one is the denominator, all right, and the first one is the numerator, N, D. So just go down the denominator column up to 5, all right, 5, and then go down the numerator, which is 2 in this case. So here's our 2. So that means we will have to look at these values here. All right, this is the set of values for a numerator value of 2. Here, let me pull up my pointer. For a numerator value of 2 and a denominator value of 5. All right, but we are looking for an alpha value of 0.025. So here is 0.025. Just a second. Here is 0.025, right? 0.025. Let me pull up my pen. 0.025. So our F value will be 8.43. All right, it's going to be equal to 8.43. So this is how you're going to look up the table for F values, right? Now we will go into discussing one-way ANOVA testing, the logic behind it. So we'll start with what it is, the logic behind it, the strategy or approach that we are going to take, and of course talk about the assumption and the distribution, the formula for F, and so on. All right, so let's proceed to that. Let's start with the assumptions or conditions for one-way ANOVA. First, like any other test or for any other test, the samples have to be simple random samples, SRS. The samples taken from the populations under consideration are simple random samples. Number two, they should be independent samples. The samples taken from the population under consideration are independent of one another. So they are not linked, they are not paired like we had learned with two population means. They are not related in any way. They are all independent samples. Number three, normal populations. For each population, the variable under consideration is normally distributed. And then number four, equal standard deviation. So the standard deviations of the variable under consideration are the same for all the populations. Again, it'll never be exactly equal to each other, but they should be close, all right, almost equal. Now let's understand what the one-way ANOVA is about. In a one-way ANOVA, what we do is we measure the variation among the sample means by a weighted average of their squared deviations about the overall mean of all the sample data. Now I understand this is a mouthful and you may not have really understood what they are talking about here, but we will go through examples and I will refer back to this slide and this definition when we work through an example. But let's do a preliminary breakdown of what they are trying to say here. All right, keep in mind that ANOVA, in an ANOVA test, we are comparing multiple means. So comparing multiple means. All right, so there can be mu1, mu2, mu3, mu4, and so on. All right, so what we do is we measure the variation among the sample means. So the whole effort exercise is to understand how these means differ and by how much, or if they don't differ at all, they are almost the same. It could also be that some of the means are equal, but others are not equal. So it could be that mu1 is equal to mu3, but mu1 is not equal to mu2 or mu4. All right, so that could be the case as well. So what we are doing is we are measuring that kind of variation among the sample means. That's what this wording means, variation among the sample means. How? By a weighted average of their squared deviations above the overall mean. So what's going to happen is, of course, we always work with sample data. From population 1, we are going to get a sample mean 1. From population 2, we are going to get sample mean 2. From population 3, we are going to get sample mean 3. And from population 4, we are going to get sample mean 4. And we are going to compare each of these sample means with each other, but we are going to look at the variation by a weighted average of their squared deviations about the mean x bar. Now you see there's no subscript to this x bar, so this sample mean over here is the mean of all the different sample means. It's the overall sample mean. If an overall sample mean calculated for all the populations put together, in other words. All right, and the way we go about it is we take each of these individual sample means, so x bar 1, and we see their deviation from the overall mean, which is x bar, all right? And then we square them. So this word here, squared deviations, we have to square them, all right? So x bar 1 minus the overall mean. There's no subscript to this x bar, all right? Keep in mind that tells us it's an overall mean. And then we square that, all right? And we also take the weighted average of it. And what is the weighted average? The weighted average is n sub 1. It's based on their sample size. And similarly, we also find x bar 1 minus, sorry, not x bar 1, x bar 2, this one, minus x bar squared multiplied by the sample size of the second sample, all right? And then likewise x bar sub 3 minus overall, and see how they vary from the overall mean, how much they vary from the overall mean. And then you will see in the formula, we will add up all these variations, all right? We will add up all these variations, and that will give us a certain matrix which will be used to find the f value later on. So we are not going into the details right now, but this was just to explain to you what this wording means, and we will come back and refer back to this again once we go into an example and discuss this in further detail. Now, in summary, what the ANOVA test does is it provides methods for comparing several means, that is, the means of a single variable for several populations. So just like in chapter 10, when we were talking about the difference of two means, we were comparing just two means. Here in ANOVA test, we will be comparing several means, but it's going to be the same variable for all the populations that we are studying. Okay. So what process do we follow? Again, when there are several means that we are comparing, there are going to be several populations. In this example, or in this chart, we have 4 populations, and we are studying something about 4 different regions in the countries. It says here, households in the Northeast, households in the Midwest, that's population 2, households in the South is population 3, and households in the West is population 4. So we have 4 different populations. From each of these populations located in different sections of the country, in different regions of the country perhaps, we select a sample of households. So the first sample is comprises households in the Northeast, sample 2 households in the Midwest, and so on. And then once we get our sample, we take our measurements, we do the descriptive study on these samples, each of these samples, and we come up with x bar sub 1. That means a sample 1 associated with sample 1. So it's the sample mean from sample 1, sample mean from sample 2, sample mean from sample 3, and so on. And once we have all our means, we will end up comparing the 4 sample means and come to a decision about the wider population. So that's going to be our strategy. And as you can see, as you may have noticed, that it's very similar to what we did in chapter 10, but chapter 10 was only about 2 populations. So we had just worked with just 2 populations. In this case, we have more than 2 populations. It's 4 populations for this particular example. We will now talk about the F statistic, the formula that we will use to find an F value. Previously, you learned the formula for the Z value. The Z test statistic was x bar minus mu over sigma divided by square root over n. For the t value, it was x bar minus mu over s divided by square root over n. And for the chi-squared distribution, the chi-squared formula was sigma o minus e whole square divided by e, correct? So for the F statistic, the formula is MSTR divided by MSE. So it says here the F statistic compares the variation among the sample means, and that's called MSTR, to the variation among the samples MSE. Now, MSTR stands for treatment mean square. All right, it stands for treatment. So TR stands for treatment and then mean square or square of means. You can say it either way. All right, it's either treatment mean square or you can say treatment square of means, and MSE is error square of means. All right, this stands for MSE stands for error square of means. All right, now MSTR has its own formula, all right, and so does MSE. So to find MSTR, we have to run through another formula for MSTR, and likewise for MSE, we will have to run through another formula to first find MSE, and then we can do this division MSTR over MSE to find the F value. Again, we will go through an example and work through the process completely, all right, and show all the steps. It's a little bit long process, but it's not a difficult process. Okay, so let's look at what we just discussed, mean squares and F statistic in a one-way ANOVA. MSTR, like we said, was the treatment mean square. MSTR is the numerator in the formula for the F value. So we had, if you recall in the previous slide, we had MSTR, which is treatment square of means, over MSE, which is error square of means. All right, and I said MSTR has its own formula, which is SSTR divided by K minus 1. And MSE has its own formula again, which is SSE over N minus K. So in order to find a value for MSTR, we have to find SSTR and divide it by K minus 1. To find MSE, we have to first figure out what is SSE and then divide it by N minus K, and then we can do the final division to get our F value. So in the next few slides, we will learn how to, first of all, what is SSTR, and then how to calculate the SSTR. It's going to be done through a table and then divided by K minus 1, and then same thing about SSE, error sum of squares is what it's called. SSTR stands for treatment sum of squares and SSE stands for error sum of squares. And we will talk further how to find K and N. All right, so let's read through it. Treatment mean square or MSTR is the variation among the sample means. MSTR goes with this formula, SSTR divided by K minus 1, where SSTR is the treatment sum of squares and K is the number of populations under consideration. So K represents the number of means that you are comparing, the number of population means that you are considering. So if it's 4 means you're comparing, then K is going to be 4. If you're comparing 50 means, then K is going to be 50. That's how it works, all right? The other one is the error mean square, or MSE. It's the variation within the samples. MSE is equal to error sum of squares, or SSE, divided by n minus k, where SSE is the error sum of squares and n is the total number of observations. So n represents the total sample size, all the samples combined together. So if there are 4 samples, then it's n1 plus n2 plus n3 plus n4, which is equal to n. All right. And k, as we know, represents the number of populations we are comparing. If it's 4, then k will be 4, so it will be n minus k. And this is the formula. SSE over n minus k is the formula for MSE. And finally, once we have our MSTR and MSE values, we will find our F statistic by dividing F equals MSTR divided by MSE. So F represents the ratio of the variation among the sample means to the variations within the samples. All right. So let's go through an example to understand exactly how to do these calculations. Here we will look into the formula for SSTR. Now SSTR, which is the treatment sum of squares, has this formula: n sub 1, which is the sample size of sample 1, times x bar sub 1 minus the overall sample mean squared, plus n sub 2 times x bar sub 2, which is the sample mean, sample mean 2, the sample mean from population 2, minus the overall sample mean squared. And you keep doing that for all the sample means, and then you sum them up. Now, if you recall that particular slide where we talked about the variation of each individual sample mean from the overall mean squared, and also weighted by its sample size. All right, that is what SSTR is. All right, so we will work this through a table which I will show you shortly. But this is how we calculate our treatment sum of squares. So you see over here we have squared the differences between the individual sample means and the overall mean, and then we've squared it, and then we have also weighted them by multiplying by their respective sample size values, and then we have summed them up. So that's what treatment sum of squares mean. For the MSE, or the error mean square or error square of means, it's a measure of variation within samples. All right. Basically think of it as the standard deviation within each sample. All right. So it's the measure of variation within samples divided by or it's not divided by, I'm sorry. It's a measure of variation within samples, or the pooled estimate of the population variance sigma squared. All right, variance is the standard deviation squared. All right, variance is nothing but the squared form of the standard deviation. Before we take the square root to find the standard deviation, whatever value we come up with is called the variance. And then once we have our that's what MSE is, but the formula to find MSE is SSE, or error sum of squares, divided by n minus k, where n represents the total sample size, all samples put together. represents n, the sample size, minus k is the number of means that we are comparing, or the number of population in our study. Now this is the example problem we are going to work on. This problem measures or rather compares the energy consumption in different regions of the country, right? So it says here the Energy Information Administration gathers data on residential energy consumption and expenditures. Suppose that we want to decide whether a difference exists in mean annual energy consumption by households among the 4 US regions of Northeast, Midwest, South, and West. So here we have 4 populations. By dividing the country into 4 regions, the Northeast, the Midwest, South, and West, and we have the data here is the consumption, the energy consumption and expenditure in each of these different households obtained from these different regions. All right. So for Northeast, it has the values 13, 8, 11, 12, 11. So we see here we have 5 samples under Northeast. In the Midwest, we have 6 samples, 15, 10, 16, 11, 13, 10. So let me write those samples sizes. All right. So for the first one, it's N1 equals 5. For the second one, N2 equals 6, right? We have 6 data points under Midwest. For South, it's N3 equals 4, and N4 is West, which is 5. All right? So each of these our regions represent the population. Population 1, population 2, population 3, and population 4. And from each of these regions, from these populations, we have gathered a sample, random sample of 5 households under Northeast, 6 households under Midwest, and then 4 under South, and 5 from the West. And their sample sizes are listed here. And they have also calculated the means, sample means, and actually there should be a line, somehow it doesn't appear. All right, it's x bar sub 1, x bar sub 2, x bar sub 3. Somehow the dash is not appearing well, but these are the sample means. So how did they get the sample mean of 11? They added all these values and divided by the sample size. So that gave them 11. So it was 55. If you sum up 13, 8, 11, 12, and 11, you'll come up with 55. And 55 divided by 5 is 11, right? We still use that same formula for mean, sigma x divided by n. All right, so that's our formula to find the different sample means. All right, for Midwest, the sample mean is 12.5. For South, it's 7.5. West, it's 7.2. All right, so step 1 is to make sure our assumptions are met. But let's look at what it says here. Step 1, independently and randomly take samples of households in the 4 US regions. All right, so these are all independent, like Northeast households have nothing to do with the Midwest households, or the South households in the South, or the households in the West. They have no relation whatsoever. They are completely independent of each other. All right, and they are randomly selected households. Now, step 2 is to compute last year's mean energy consumption. I guess this data is from the previous year, the year before the study was done. So once you collect your data, you have to do your descriptive study on it and come up with the sample means as well as the standard deviation, but we don't need it right now. All right, we'll be calculating that later. So these are all the means. Here are all the sample sizes. We'll now go over the process of finding SSTR, which we need to find MSTR, which in turn we need to find the F value. Keep in mind, F has the formula MSTR over MSE, and MSTR has its own formula, which is SSTR over K minus 1, and then MSE has its own formula, which is SSE over N minus K. So in order to find the values of MSTR, we first have to find SSTR. Now this slide goes through the process of finding SSTR through a table. But let's just write the formula for SSTR. The formula for SSTR is sigma n sub j times x sub j minus x bar whole squared. Let me explain a little bit what this n sub j and x sub j represent. N sub j is all these individual sample sizes in each region, right? So we have in the first column in the table the regions listed, and then in the next column we have the related sample sizes, and J represents, it tells us which sample size we are talking about. Since we have Northeast first, N sub J would be N sub 1, and then Midwest would be regarded as N sub 2, N sub 3, and so on. All right, so J essentially just indicates which particular sample size we are referring to. Same with X sub j, because we have 4 different sample means for each region. The J, whatever, we can put in whatever value, we can put in a value for J from 1 through 4. So X sub 1 will represent the Northeast region, X sub 2 will represent the Midwest, and so on. That's how it's going to go. And then, of course, we have to square it. Keep in mind that we had previously defined SSTR as how much the individual means of each region vary from the overall mean, and then it's actually the squared difference, right? X sub j minus x bar, since we are subtracting them, it represents a difference, and it's not just a difference, it's the squared difference. And we also said that it's going to be the weighted squared difference. And how do we weight them? We weight them by their individual sample sizes. All right, so let's run through this table to see how we satisfy this particular formula and come up with a final value for SSTR. So in the first column we have all the regions listed. In the second column we have all the sample sizes listed. Now these were all given to us. In the third column we have the individual sample means, right? X sub j means all the individual sample means. Now the next column is calculating the difference of each individual mean and the overall mean. So I'm going to put a bar over this x here. It's going to be x sub j minus x bar. So we have our x sub j values, but we do not have our x bar values. Now there are 2 ways to find your x bar, that is the overall mean. All the data points for all the regions put together represents the total sample mean, in other words, right? Now if you are given the individual data points for Northeast, Midwest, South, and West, all the individual data, then you can just add them up and divide them by the total sample size. Right over here, the total sample size, as you see, is 20. If you sum up all the n sub j values, the total is what n is. All right, that n equals. All right. So if you're given the individual data points, you can sum them up. It's a little bit longer process. However, another way of doing that, and especially if you do not have the individual data values and you're just given the sample means, in order to find x bar, this is what you have to do. It's sigma, all right, sigma n sub j multiplied by x bar, x bar sub j. This is all actually x bar sub j as well. Let me see if I can write it. It's x bar sub j, all right, x bar sub j. N sub j multiplied by x bar sub j over n, and that n in the denominator is the total sample size. All right, so what this means is, what we need to do here is take each sample mean and multiply by its corresponding sample size, and then add them all up and then divide by the total n. So this is how it's going to run here. And for the first one, it's 5 times 11, right? N sub 1 is 5, so it's going to be 5 times the sample size for the Northeast plus 6 times the sample size for the Midwest plus 4 times the sample mean for the South, which is 7.5, plus 5 times 7.2, right? So we multiply each of the individual sample means by their respective sizes and then divide by the total sample size, which is 20. All right, and when we do that, we will get the overall sample mean, which will come out to 9.8. You can do this calculation on your calculators. You should come up with an x bar value of 9.8. So once we get our value for x bar, and I'm going to write that down here. It's going to be x sub j minus 9.8. So we have to take our individual x sub j values in this case. In the first case for Northeast, it's going to be 11 minus 9.8 gives us 1.2. And let me just be a little bit clear and write it x sub j bar. All right. And then 12.5 minus 9.8 is 2.7. 7.5 minus 9.8 minus 2.3. That's how it goes. Now, once we calculate all the differences of the individual means from the overall sample mean, all right, we have to square them. All right, we first have to square them, and remember, when you square any value, whether positive or negative, you should always get a positive value. So over here, these values are all positive, and once we square them, we have to take the weighted average by multiplying each of these values by their respective sample sizes. So the way we got 7.20 is 5 times 1.44 n sub j multiplied by the previous column x sub j. So somehow the bars are missing. Okay, then it's 6 times 7.29, which gives us 43.74. Again, go to the third one, which is South, n sub j, that is 4 times 5.29, gives us 21.16. So once we do all those calculations, we just need to sum them up, and that's going to be our SSTR. So what we did was just run through this formula step by step through this table. All right, first we found our x bar. All right, then we subtracted the individual means from the x bar values, and then we squared squared each of these values, and then we multiplied them by their respective sample sizes and came up with an SSTR value. After summing up all the values in the last column, we came up with an SSTR value of 105.90. To find the MSTR, you have to take your SSTR value you calculated from the table and divide it by K minus 1. What is K? K represents the number of regions in your study. So we are comparing the means of 4 regions. So K represents 4 here. So it's going to be 4 minus 1. So 105.90 for SSTR, which we just calculated, divided by 4 minus 1, which is 3. And we should get an MSTR value of 35.3. So here in this process, we just calculated what MSTR value would be. Now we have to run through a process where we will be calculating MSE, but first we need to find SSE, and then we'll divide it by N minus K to come up with SSE, and only then we can get our F value. Now here we'll go through the process of finding SSE, which in turn will help us find MSE, and therefore this will lead us to complete the calculation of the F value. So let me write the MSE formula once again. MSE is SSE over N minus K. All right. Now SSE has its own formula, which is sigma N sub j minus 1, N sub j minus 1, and then S sub j squared. All right. That's our error sum of squares. Again, we'll work through it using a table. In the first column, we have all the regions listed and then all the sizes listed. However, here we don't have to consider the means because this is only about the variance, the standard deviation, so to speak. However, in the third column, it's not the standard deviation values, it's the variance. And what is variance? Variance is the squared form of the standard deviations. Now, if they give you the standard deviation, just the standard deviation, then you will need to square them in order to complete the process. All right, keep in mind that variance is the squared form of the standard deviation. If you just use the standard deviation values given to you, it will not be the correct answer. All right, you'll get a wrong answer, and therefore the further calculations will also be wrong. So make sure that you are squaring your standard deviations when you are working through this. We are working with variance here. However, if you are given the variance, then just use them as given to you. All right, so here we have again the region, the sizes, the variance. If they give you the variance, just list them here in the third column. If they just give you the standard deviation, then just square your standard deviations and then list them here. The next part, the next column says N sub j minus 1. Since we are dealing with samples here, we always use N sub j, that means sample size minus 1. All right, for when we work with samples. So it's basically 5 minus 1, 4, 6 minus 1, 5. So it's 1 less than whatever the sample size, original sample size is. And once you find the values in the fourth column, you just multiply them with the variances and then you sum them up. So 4 times 3.5 is 14. 5 times 6.7 is 33.5. 3 times 9, 27. So that's how we come up with the values, and then you sum them up and you get your value for SSE, which is 89 minus 3. All right, so that's SSE. And then in the denominator, to find the MSE, you need to divide SSE with by n minus k. What is n? N is your total sample size, correct? So n is going to be 20, and then k represents the number of means you are comparing. We already used a value for k in the previous slide when we calculated SSTR, so, or MSTR really. So 20 minus 4 is, okay, 20 minus 4 is what we are going to use in the denominator to find our MSE value. So 89.3, which we obtained from the table, calculations from the table, and then divided by n minus k, which is 16. So we get an MSE value of 5.581. And then finally, when we have our MSTR and MSE values calculated, the rest is easy. The formula for F is MSTR divided by MSE. Put in the value of MSTR, put in the value for MSE, divide them, and you come up with a value of 6.32, and that's your F value, your F statistic value. All right, so that is the process you will be going through in order to find F. First, you have to find MSTR, and the MSTR itself has its own formula, which is SSTR divided by K minus 1. And then you have to find MSE. In order to find MSE, you have to find SSE. And you use that table to find SSE, and then divide SSE by n minus k to come up with your MSE value, and then just plug in those values into the formula for F and you get your answer, right? Now in the next few slides, we're going to go over some theories and facts about the ANOVA procedures which we can apply to make our calculations faster and more efficient. First, let's go over the distribution of the F statistic for a one-way ANOVA test. It says here, suppose that the variable under consideration is normally distributed on each of k populations and that the population standard deviations are equal. Then for independent samples from the k populations, the variable F equals MSTR divided by MSE. We already went through this formula before, but let's look at the DF here. It says it has the F distribution with DF, degrees of freedom, equals k minus 1 comma n minus k if the null hypothesis of equal population means is true. Here n denotes the total number of observations. Remember when we were talking about the F statistic, the F distribution at the beginning of this chapter, we saw that the DF of those curves had two parameters, correct? There was the DF with two parameters, or something like maybe 2,7 or I don't know, maybe 3,10 and so on, right? And we said the first one is called the numerator parameter and the second one is called the denominator. The denominator parameter of the DF. What is the formula for the numerator parameter? It's k minus 1, which we used to find MSTR. If you recall, the formula for MSTR was SSTR divided by k minus 1. That was the DF. That's the numerator DF, because we use that to calculate the numerator of the F value. Likewise, for MSE, the formula was SSE divided by n minus k. That is what we use to find the denominator of the F value. And that's the reason we call these two parameters the numerator and the denominator. Again, the DF of any F value has two parameters. One of them is called the numerator. The first one is called the numerator, and that goes with the formula k minus 1. And the denominator has the formula n minus k. And k represents the number of means that we are comparing, therefore the number of populations in our study, and n represents the total sample size, in other words, total number of observations. We'll now discuss a very important identity which is used to speed up the process of calculation of the F value in an ANOVA, one-way ANOVA test. It goes by this equation which says SST, that means total sum of squares, all right? So SST stands for total sum of squares. Sum of squares is equal to, SSTR already is treatment sum of squares, right? So it's equal to the treatment sum of squares plus error sum of squares plus error sum of squares, all right? Sum of squares. Now, the way it helps in speeding up the process of calculation is it's easier to find SST and SSTR, and once we have those values, then we can just plug them into this equation and solve for the missing value SSE. So I'm going to go through an example using the computational formulas. In the next slide, we will see some computational formulas to calculate SSTR, SST, and SSE. And once we combine the computational formulas as well as this identity, it'll be much faster to come up with the F value. Here we see the formula for SST, the total sum of squares given to us. What is it? It's a sigma x sub I minus x bar whole squared. What is x sub I? X sub I represents the individual values in our data. All right, so how much the individual values vary from the overall mean. It's not the separate or the individual sample means, all right? That's SSTR. That goes in the SSTR calculation. These for SST, X sub I represents the individual data points in our data of all the populations put together, of all the samples put together, and we calculate how they vary from the overall mean. So it's the sum of the square difference of the individual data points from the overall mean. That's SST, and that value will be equal to SSTR plus SSE. So again, here we have in pictorial form the relationship between the total sum of squares SSTR, which is equal to SSTR and SSE, all right? So it's SSTR plus SSE is equal to the total sum of squares SST. Now, since the ANOVA analysis comprises of a lot of different calculations, we often represent them in an ANOVA table. So in this table, we have a column for the source, that means which happens to be the treatment and the error. Treatment is TR, right? It's TR, and for error, we use the letter E. And the DF for the treatment is K minus 1. Remember, the final formula is MSTR, and then we have MSE for the error. The DF, we start with the DF in the second column. That's K minus 1, that is the number of populations, also called number of treatments, minus 1. And DF for the error is N minus K, which we use in the denominator. And when we sum them up, it should be N minus 1. All right, the total of the DFs should amount to N minus 1. Then we have a column named SS, and if it's the treatment, it becomes our SSTR value. If it is error, then it's going to be SSE value that we found previously from our calculations using the tables. And then we have a column for MS, which involves the SS divided by the degrees of freedom. If it's MSTR, then we divide it by the degrees of freedom, which is K minus 1, which is also the numerator parameter of the DF. And for MSE, it's SSE over N minus K, which represents the denominator parameter of our DF. And finally, once we have the MSTR and MSE values calculated, F will be equal to MSTR divided by MSE. So the final column is that for the F statistic. And over here in this column for the SS, we have SSTR and then SSE, and the total of SSTR plus SSE should give us SST, the total sum of squares. Here they filled in the values in the table, into the ANOVA table, the values that we calculated previously. You see the first column is just specifying which row is for treatment and which row is for error. And then the DF was K minus 1, so 4 minus 1. We had 4 regions, so 4 minus 1 is 3. And then the DF for the error was N minus K, which was 20 minus 4, right? There were 4, the value of K was 4 and N was 20. So 20 minus 4 is 16. And when you sum them up, you should come up with N minus 1. So 20 minus 1, which is 19. Then we found the value of SSTR. The first row represents SSTR, and we calculated that value to be 105.9. That came from the calculations in the first table. And then for SSE, we came up with a value of 89.3. When we sum them up, we get a value which is equal to SST. So here we have, this is TR, this is SSTR, this is SSE, and this one is total SST. Let's surround this with brackets. All right. And then for the MS column, which is SS divided by DF, when we divide 105.9 by 3, we came up with 35.3. Likewise, when we divided 89.3 by 16, we came up with 5.581. And finally is the value of the F statistic by dividing 35.3 with 5.581. We came up with a value of 6.32. Now these are the formulas to find the sum of squares, the different sum of squares, the total, the treatment, and the error. But we have two different formulas here. The defining formula is what we use so far to find our MSTR and the MSE by first finding SSTR and SSE. We didn't need to find the SST because if we had the SSTR and the SSE, we could just use the formula for MSTR and MSE to find the value of F eventually. However, for the computing formula here, which is a much faster way of performing a calculation, when we have several more, like when we have a high volume of populations to compare, then with a lot of data points in it, then the computing formula is definitely much faster. And in that case, rather, it's better to first calculate our SST and then the SSTR, and then use the identity that we learned before to find SSE. All right. So you can go through this table. It's in the PowerPoint slide. It's the different variables are explained here as well, but I will go through an example problem and work out a problem using the computing formula. What we learned so far was using the defining formulas. Now let's go through the process of ANOVA test in its entirety. First, the different assumptions that need to be satisfied for an ANOVA test are: it should be simple random samples, it should be independent samples, it should be normal populations, and equal population standard deviation. All right, if not exactly equal, then close. The way we state our hypothesis for an ANOVA test is: null hypothesis should state mu1 equals mu2 equals mu3 equals however many mu's you are comparing. However, the alternate hypothesis must say not all the means are equal. Now, you cannot just say mu1 not equal to mu2 not equal to mu3. That's not the correct way of phrasing the alternate hypothesis. You have to put it in this form, in this sentence form, because when we say not all the means are equal, what we mean is there could be some means that are equal. So mu1 may be equal to mu3 but may not be equal to mu2. So when we say not all the means are equal, we are saying that the means, some of the means could be equal, but not all of them are equal. Whereas if we say mu1 not equal to mu2, not equal to mu3, and so on, that means that none of the means are equal to each other, which can be a fallacy, right? For step 2, we decide on the significance level alpha. For step 3, we calculate our F statistic, the evidence, the test statistic, which is given by the formula MSTR divided by MSE. However, please note that MSTR has its own formula, which is SSTR over K minus 1, stated in this ANOVA table, and MSE has its own formula, which is SSE over N minus K. So we have to go through a process for that calculation, and then once we do that, we can construct our ANOVA, one-way ANOVA table, and then we go on to performing the test using the critical value approach or the p-value approach or both. Then we come to a decision, and then finally we will interpret. Now keep in mind that the F distribution is a right skewed, right? F distribution is right skewed. Right? It's a right skewed distribution. Therefore, our hypothesis test will always be a right tail test. All right. So even though the alternate hypothesis says not all the means are equal, but because we are using the F curve, the F distribution, the test will be a right tail test. So here is a continuation of the process of hypothesis test. You see over here, we have to find, for the critical value approach, we have to find the cutoff between the reject region and the do not reject region. And keep in mind the DF has two parameters in it, K minus 1 and N minus K. K minus 1 being the numerator value and N minus K being the denominator value. And if you're using the p-value approach, then again, the same thing, but you are using your F statistic value that you came up with from your calculations. Represent that on your F curve, show where it may be located. And because it's a right tail test, the p-value is going to be the area to the right of wherever your test statistic F value is located on the curve. All right, and then finally, step 5 is for critical value approach, we determine in which region the test statistic falls and take a decision accordingly. But for the p-value approach, you compare p with alpha. If it is less or equal to alpha, the significance level at which we are testing, then we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. And the final step is always to interpret. It's the last step, but not the least. It's a pretty important step to interpret the results of the hypothesis test correctly and in context of the problem. So let's finish off this problem that we were formulating. Again, we are comparing the energy consumption between the different regions of the United States. The 4 regions were Northeast, Midwest, South, and West. So we are going to collect these were the samples collected from each of these regions, and then we take the measurements by region, and now we are going to compare their means to see if their means are all equal to each other or some of them are different. Okay. The first thing is to check the assumptions. It has to be a simple random sample. So somewhere in the question, it may be saying that it's a simple random sample, and it should. Otherwise, we cannot perform any statistical study if the data is not based on a simple random sample. They have to be independent samples. They have to be normally distributed, the variables, and then they have to be the population standard deviations are equal. Let's just assume that they are equal in this case. And it says here the ratio of the largest to the smallest standard deviation should be less than 2. So we just have to check on that to decide whether the population standard deviations are almost equal or not. So that's going to be kind of the yardstick that the ratio between 2 standard deviations should be less than 2. Now we are going to begin with the first step of any hypothesis test, which is to state the null and alternative hypothesis, right? So here it says let mu sub 1, mu sub 2, mu sub 3, and mu sub 4 denote last year's mean energy for households in Northeast, Midwest, South, and West respectively. Note that they have all used the population means here because we are stating our hypothesis, and we should always state our hypothesis with the population mean symbols, all right, in terms of the population. So the null hypothesis is going to state that mu sub 1 equals mu sub 2 equals mu sub 3 equals mu sub 4. Whereas the alternate hypothesis has to be stated in a phrase, in a sentence. We have to say not all means are equal. Again, like I said before, we cannot write it as mu sub 1 not equal to mu sub 2, not equal to mu sub 3, not equal to. This is not the right way to state the alternate hypothesis, because when we do it this way, it tells us that none of these none of these means are equal to each other. Now, it is possible in an ANOVA test that some of these means are equal to each other or close to each other, but some of them are different. All right, so to state it, to imply that, we have to say in words, not all means are equal. This is the best way to state it. Then it says decide on the significance level alpha. The question says at the 5% significance level, do the data provide sufficient evidence to conclude that a difference exists in last year's mean energy consumption by households and so on. So we are using the 5% significance level, therefore alpha is going to be 0.05. Okay. We are now in step 3 of the hypothesis test, where we find the test statistic value, the F value in this case, because we are using the F distribution, and we use the formula MSTR over MSE, which is a formula to find the F value. Now we've worked the calculation step by step previously, so please look back this video to find where we did the calculation and you can go over that. But let me just quickly recap a little bit about this formula. Remember, MSTR had its own formula, which was SSTR divided by K minus 1. And likewise, MSE too had its own formula, which was SSE over N minus K. Now, SSTR stands for treatment sum of squares. And treatment sum of squares was calculated using this formula. Let me write that down here. SSTR equals sigma n sub j times x bar sub j minus x bar squared. What that means is that we take each individual sample means and find how much it is off from the overall mean. So that's why it's individual sample mean minus the overall sample mean, the variation of each individual mean from the overall mean. And then we square that, and then we take its weighted average by multiplying it by its respective sample size. And once we get that value, we sum up all the uh, all the uh, all the values that we found, and that will give us the SSTR. SSE, on the other hand, goes by this formula here. It's sigma n sub j minus 1 times S sub j squared. Now remember, S sub j squared is the standard deviation squared. So we take each individual standard deviation and square it to find the variance. So whenever the standard deviation is squared, it's called the variance. And we multiply again each of them by n sub j, the respective sample size, minus 1. Again, that's weighted. And then we take the sum of it, and that gives us the SSE. What about K minus 1? K minus 1 is the DF for the numerator, right? So we divide SSTR by K minus 1. K represents the number of means we are comparing. So what is K? Number of means, and therefore the number of population. All right, or let's put it as number of population means we are comparing. Number of population means being compared. And all right, and N is the overall sample size. So once we know what our K is, we know what our N is. For the denominator DF, degrees of freedom, we just do N minus K and divide SSE by that quantity. And once we get our MSTR and MSE values, we divide them to get our F values. Again, please look back this video for where we did the calculation to see how we went about it, how we walked through the table to get the F value. So we will have an F value of 6.326. So when we did the calculations, our MSTR value, so let me write that down, F was equal to MSTR was 35.3 and our MSE value was 5.58. When we did the division, we came up with a value of 6.326, and that was our F statistic value, F sub 0, which is our test statistic or the evidence. Step 4 is to use the approaches to help us come to a decision. The critical value approach is where we uh, create our reject and do not reject regions. Now, remember that the F distribution is a right skewed distribution, therefore, and it's anchored at 0. Its lowest value is a 0. So start your curve. When you draw your curve, start from 0, make it a little bit right skewed. That means peak will be to the left. All right, and F distribution, since they are right skewed, the hypothesis test will always be right tail tests. All right, so we have to mark our reject regions. So here's our reject on the right hand side, again because it's a right tail test, and on the other side, left hand side, we'll have our do not reject regions. We need to find our critical value. Now the area associated with the reject region is alpha equals 0.05 because we are testing at the 5% significance level, but we have to find our F of 0.05. Our critical value is F of 0.05, and our DF is, or rather with DF, all right, with the DF equals 2 parameters for the DF. One is K minus 1, which is 4 minus 1. All right, 4 minus 1 is 3, and the other one, n was 20, so 20 minus 4 is 16. So the two parameters, numerator is 3 and denominator is 16. So if you look up your table, or if you are using your calculators to find the F value, then you should come up with an F value of, let me just look it up here. Just a second, what our F value is. .24. So the F of 0.05 with DF equals 3 and 16 is 3.24. All right, it's 3.24, and that's our critical value. CV is 3.24. This is our CV, critical value. So I'm going to write 3.24 here, but now we are going to bring our test statistic value. So F sub 0 was 6.32, and it falls way to the right because it's greater than CV of 3.24. All right, so it'll fall somewhere even further out to the right probably, but let's just show it here. 6.32 falls in reject region. Falls in reject region. Therefore, decision is reject null hypothesis. Reject the null hypothesis. Now let's do the same thing using the p-value approach and see whether we get to the same decision. Now let's do the same test using the p-value approach. So I'm going to first draw our diagram here for the p-value approach. Again, this time we will use our test statistic value, which was F sub 0 equals 6.32, and indicate that on our on our diagram here. All right, so it'll be located, let's say somewhere here. I don't know, let's just put it here. So the area on the right, because it's a right tail test, it'll be the area to the right of wherever the test statistic value is located. That's going to be our p-value, right? Now, if we look at our uh, if, or if we use our calculator to find the p-value for the F statistic, we will have to specify both the numerator and the denominator uh, DF values, right? So what we are doing here is find area, find, oops, let me write it clearly, find area to the right of F sub 0 equals 6.32 with df equals, now our df's were k minus 1, which was a 3, right? We had 4 categories, so 4 minus 1, 4 regions in fact, so 4 minus 1 was 3, and n was 20, so 20 minus 4, right, was 16. So df's of 3 comma 16, and when you run that, you can if you're using the table, of course it'll be an estimated uh, value, but if you're using a calculator or statistical tool, then it'll be an exact value, and that comes out to a p-value of 0.0049. And in the next step, you compare p with alpha, right? So P is 0.0049. It's definitely less than our our alpha value. Significant level was 5%, so alpha would be 0.05. If it is less, we reject our null hypothesis, which matches with the decision we got from our critical value approach. Right? So now we can go ahead and formally state our decision and then interpret the test. As we saw from our approaches, we came to the decision to reject the null hypothesis. Therefore, you're going to state reject null hypothesis for the decision. Reject null hypothesis, and you're going to interpret. And that's step 6. You have to interpret, even if the question doesn't ask you to or prompt you to do the interpretation, please go ahead and interpret it, because a hypothesis test or a confidence interval is not complete without an interpretation. So for the interpretation, we are going to say at the 5% significance level, 5% significance level, the data do provide sufficient evidence. The data do provide sufficient evidence to conclude evidence to conclude. And then I'm going to take the wording from the question to conclude that a difference, everything from after conclude, all right? So to conclude that a difference, I'm going to just copy it verbatim, a difference exists in last year's mean energy consumption by households among the 4 US regions. Okay. So that's how we perform an one-way ANOVA test. Now, the last section of this chapter is going to be on multiple comparisons. It's called multiple comparisons because we are comparing multiple means, and the way we do the comparison is by finding confidence intervals, right? So we will go into that. However, let me tell you that this chapter will uses a different distribution, but we do not have the table for that distribution. So we are not going to get any questions on this on tests and assignments, but we are definitely going to go over it and try to understand how the multiple comparisons are going to be done. Here's an outline of the comparison method, and it's called the two-key multiple comparison method, right? And it's about finding confidence intervals, but we are taking two means at a time to find the confidence interval. So it'll be quite a few confidence intervals that we will have to calculate. So we have our assumptions, which are similar to what was in the case of hypothesis tests. Step one is to decide on the family confidence level 1 minus alpha. All right, so we are using the confidence level is 1 minus alpha like with any confidence level, but because we have multiple comparisons here, we use the word family confidence level. Step two is to find Q sub alpha for the Q curve with parameters kappa equals k and nu equals n minus k, where n is the total number of observations, right? So we are not provided the table for the Q distribution, but it's kind of similar to the F distribution, right? And then once we find our Q of alpha, we go on to the step three of calculating, or rather finding the endpoints of the different confidence intervals. So this is the formula for that. And finally, we declare two population means different if the confidence interval for their difference does not contain zero. Otherwise, do not declare the two population means different. This is similar to what we have been doing whenever we compare two means, two population means, or two proportions. Remember, if we said that if one end of the confidence interval is negative and the other end is a positive, that means it contains a difference of zero somewhere in between the interval. And if the difference, so all this represents difference, correct? All comparisons are about differences between two means or multiple means. And if the difference between two values is zero, that means there's no difference between the values we are subtracting. So that's the logic we are using to conclude if a difference uh, exists between two means or not, right? And then step five is to summarize the results in step four by ranking the sample means from smallest to largest and by connecting with lines those whose population means were not declared different, and finally interpret the results of the multiple comparison. So what I'm going to do in the next few slides is to show you the results of the confidence interval, and then for all the different regions, and then we will decide which of them are equal or different, or if they are different. So again, what is a multiple comparison? A multiple comparison is often needed to determine which means are different, which mean is largest, or the relation among all the means. Methods for dealing with these problems are called multiple comparison, and the method we just learned is the two-key multiple comparison method uh, that we are using in order to figure out the differences. And like I said before, we first determine the confidence intervals for the differences between all possible pairs of population means. And then once we find the confidence intervals, we look at their endpoints. If two means are declared different, if or rather the two means are declared different if the confidence interval does not contain a zero, right? Now for the confidence level in a Tukey method, there are two types of confidence level. One is called the individual confidence level, which is the confidence we have that any particular confidence interval contains the difference between the corresponding population means. And the other one is the family confidence level, which is the confidence we have that all the confidence intervals contains the differences between the corresponding population means. Since we use the Q distribution for the Tukey method, let's just go over the Q distribution properties. It says here variable has a Q distribution if its distribution has the shape of a special type of right skewed curve, which is the same as the F curve, but this is called a Q curve. A particular type of Q curve has two parameters, and that's also similar to the F curve, but in the case of Q curve, it's called nu and kappa. So the first parameter is called nu and the second one is called kappa. Now this slide is about reading the Q tables, and it's read pretty much the same way as the F distribution. However, we need a Q table given to us or provided to us in order to calculate or find the Q value, but the process is the same, right? So now we are going to proceed on finding the confidence interval between uh, between the different regions, right? So the way it's going to work is we are going to take a or find a confidence interval between northeast and midwest, and then northeast and south, and then northwest, east and west, and then midwest and south, midwest and west, and then south and west. All right. So there are going to be a lot of confidence intervals that we are going to find. Again, we are comparing means, therefore we are interested in differences, and therefore we will take two means at a time and find the differences until all the means are compared, until we find the confidence interval for all combination of these regions. Now here we have all the calculated values of the confidence intervals, and we put them together in a table, and it's a matrix, a 2 by 2 table, and the placement of the confidence interval shows which two regions we have taken the difference of. So for Midwest and Northeast, we have the confidence interval, the difference of their means were negative 5.60 to positive 2.60. Likewise, the difference between the south and northeast was negative 1.04 and 8.04, and so on. That's how we should be reading this table. Now, let's look at the confidence interval endpoints and try to determine if there is a difference between the means of the two regions or not. For the first one, it's negative 5.60 and 2.60. Now that interval, negative 5.60 and 2.60, contains a difference of 0 somewhere in the interval, right? In the middle of the interval rather. So when the difference is a 0, when the difference of two quantities is a 0, that means the two quantities are the same, correct? So that means there's no difference between the two quantities, they are equal. So that's how we determine if the means are equal or not equal, or if they are different or not. So let's look at the interval for the south and northeast. It's negative 1.04 and positive 8.04 on the other end. This 2 contains a 0. There's a 0 in the interval. Therefore, the conclusion should be there's no difference between the two means. West and northeast, again, there's a negative on the lower end and a positive. So whenever the ends have unlike signs, that means it contains a 0 as a difference within its interval, and the conclusion should be that they are equal. There's no difference. However, South and Midwest both have positive endpoints, right? Both the endpoints are positive values. So 0.63 positive and 9.37. So when the signs are the same for or at both ends of the interval, that means there is no uh, difference. All right, there's no difference. West and Midwest too, it's the same situation. We have two positive endpoints. There's no difference in their signs, so it doesn't contain a 0 in this interval. Therefore, the conclusion is that they are different. West and south, negative 4.24 and 4.84. Again, the endpoints have different signs. Conclusion should be that they are same. There's no difference in the mean. So that's how you read and interpret the confidence intervals using the Tukey method. So this brings us to the end of chapter 16 on ANOVA tests. Uh, we interpret the confidence interval and declare the two population means are different if the confidence interval for the difference does not contain a 0. Otherwise, do not declare the two populations different. And once we find and make that interpretation, we can put it together formally. All right. So we will now go through the worksheet for this problem. However, this example on energy consumption is an example problem in the book. You may want to read the book, go through this example and see how they worked out. They should have worked it out in a similar way, but it'll explain the um, uh, explain in further details uh, how the Tukey method works, and it may help close some gaps in your understanding.